Hello there. Today we'll be doing the least recently used cache problem. In the least recently cached problem, we are trying to store items into a cache, and we should be able to retrieve it. And if any number of items exceed our capacity, we should remove it from our cache. If we try to access it again, we should return -1 because it doesn't exist anymore. So we need to do this in O of 1 time. The way to do this, the data structure we'll be using is a linked list, because with a linked list, our hash can point to the node where we're trying to remove and add it to the end of the list. We can do this for all the items. So we will have a key that will point to a node, which the node will hold the value. Okay. So we also want our node to hold the key as well, so that we can refer, when we get the node, we can refer back to our hash. That way we have some easy access going on, two-way access. With that, I think we can begin. The explanation for a reason why we can't use an array is that it takes O of n time to add and remove. If we use a heap, it will be n log time adding and removing. So we can't use any of those. So we have to create our own data structure, a doubly linked list. So let's create our data structure first. We're going to create a class called a node. In this node, we have to define the init function and with self, and we need a key and a value. The reason why we want a key and value is because with a key, we can refer back to our hash and remove things, and and add things, and we can remove it. Another thing we want is a left and a right pointer. So left pointer is going to point to our beginning, to refer to the nodes. We can't have a singly linked list because that means that we are screwing up somewhere. Okay, maybe not screwing up somewhere. So that means we can't go. We can't take the left node and the right node and assign them to each other to remove a node that's in between. Okay. Speaking of which, let's write some pseudocode. So in the init function, we want to assign a dummy node to keep track of our items, so that it makes it so that we don't lose track of any items. And we want a hash set to point to those nodes. Okay, so let me show you what I mean. So we have a self.capacity to equal capacity. So we store our capacity. We have a self.hash set so that we can make sure that we can have instant access to any node in our cache. So then we have self dummy head equals node of 0 key, 0 value, and self.dummy tail equals node 0 and 0. With that, let's assign them to point at each other. So self.dummy head right is equal to self.dummy tail, and self.dummy tail left equals self.dummy head. So at this point, the dummy head and dummy tail is pointing to each other because there's nothing there. Now we can start inserting items, and that way they will start pointing to each other. So we know that when we get an item, we will need to add, and we also we might need to remove. I think the easiest way here is to remove it from its particular location first, and remove from linked list, and add to linked list to tail of linked list. right? And if exist. If it doesn't exist, just add it. It just remove. I mean, if it doesn't exist, if not exist, return -1. As for setting the item, if it exists, we want to remove it from our hash and our linked list, because we don't want that node anymore in our hash set. We want a brand new node. Then add whether it exists or not, add it to our hash and linked list. Afterwards, if overcapacity, we want to remove the most least recently used, because we don't want to keep that around anymore. And that means we are going to remove it from our hash set. Okay, so that means we'll be using a lot of removal and setting. So we need to create this function so that we can remove and add easily between the two items. So def remove of self and node. So to remove an item, we have the node, and we're going to set the left to point to right node, the right of the node, and the right to point to left node. Let me show you what I mean. So this is left, this is the node, this is right. They're currently pointing to each other. What we need to do is that we are going to point the right node to the left node, and the left node to the right node. Even if the node is pointing to each other, there are no references to the current node anymore, because in this picture, left points to right and right points to left. What node is doing here is that node is pointing to left and right, but if node doesn't exist anymore, I mean, like, no one's keeping track of it, we will not be able to find it. It'll just be lost in the memory. So we don't need to do anything about that. But if we do want to clean it up a little bit more, we could say node.left and node.right equals none, and then let it go. But that doesn't really matter. So let me just comment that out. And this is here's the code for it. Left is equal to node.left. Right is equal to node.right. And we're going to do right.left is equal to right.left is equal to left, and left.right is equal to right. And that's it for remove. We're done with that. Now we're going to add the item. And what does adding mean? Adding means that we are going to attach our item to the tail of our list. So we are going to set the left node to the left node, as in the dummy. We're going to set the dummy tail.left. Dummy tail.left is on the left side of the tail. So let me show you in demonstration what that means. So here we go. So we have left, and we have the dummy tail, DT, tail. The tail is pointing to each other at this point, and we're going to get the left item, so that we want to insert the new item with the left item to point to a new item, the node, and we want the tail item to point back to the node, and we want the node to point back at the tail. So that's what we want to do, and we're going to do that. So first of all, let's grab the left side. Left is equal to self.dummyTail dot left. So we got that item. So we want a left dot right to now point to the node. We want the node dot right to point to the self.dummyTail. And we want the dummy tail dot left to point to the node. I think that should be all. Yes, that should be all. Am I missing something? Oh, right. Node dot left should point back to the left. And that should be all. Okay, so we are done with that picture. So we have completed this picture, and we have completed the previous picture where we insert the node. Where we remove the node from both sides. Okay, now that we're done with the removal and the adding, let's get an item. So if the item exists, let's set that node equals self.hash set of key. So we found that our key points to our node. So when we remove that node, and we're going to add it to the end of the tail. Once that happens, now our item is our most recently used item, and we can now return the node dot val. Else, we're going to return 1, -1, and that completes that piece of the code. Okay, last bit of the code, the set. So what happens if it exists? Remove it from hash. So if key in self.hash set self remove self.hash set of key. One thing to note is that we don't need to remove it from the linked list right now. The reason being, we are going to get rid of the least recently used item. And yeah, I think it should be fine. What do I mean by that? So suppose we don't remove it from the linked list. What will happen to this item, to this linked list node? Will we ever point to it? I'm kind of worried that we might point to it. But I'm not sure. Let's just not point to, we can, well, this particular function here removes it from the linked list, but we do not remove it from the hash set. So I think it should be fine without removing it from the hash set because we're just replacing the item eventually. So, okay. Node is equal to node of key and value. And we want to add this to our linked list. And we want to reset our key to this particular node so that we can find it later. If length of self dot hash set, if it's longer than our capacity, let's remove the dummy dot write, and that by removing that item, we are completing a process to get the new head. So self and lastly, we have to delete the hash set of the last item because we don't want to be able to point to it anymore. And with that, let's run the code. Oh, syntax is wrong. Accepted and submit. And we are good. And that is how we do LRU cache. So let me just space this out, this code. And hopefully we can see it all. That's a very long code. I don't know how I'm supposed to help you see all this code. Even if I shrink this, it's not going to help in one screen. So I'm going to slide it down slowly. Okay, and that is all for LRU cache. I hope this is very good, and if you have any questions, you can answer and ask below. Maybe someone will answer it. And I would like, if you enjoyed the video, please like and subscribe. And if you want more videos, check the link in the description below. And that's all. If you enjoyed the and have a good one. I'll see you next time.